Assalamu alaikum. Welcome to the next lecture of data science. We were covering the machine learning topics in this week. So today we'll have an introduction to the artificial neural networks as part of our series of the supervised learning paradigm. So in the last lecture, what we did was we covered the k-nearest neighbors. Now k-nearest neighbor is a classification technique which falls under the category of supervised learning. It is also known as instance-based learning because in order to find the class of the test sample, we need to have all of the training samples placed in memory at any given time. So at any runtime, all of the training samples are present to us. So that's why we call it instance-based learning. There were two important aspects to k-nearest neighbors that we need to see. One, the significance of k. What value do you assign to k, which should be, and we determined that it should at least be equals to the number of classes, and it is usually taken as an odd number so that we have a tiebreaker in case all classes give the same number of votes. And the second thing that we saw was the importance of the distance metric. There was Euclidean distance metric and Minkowski distance metric. So whichever one you choose to use in the final one, would have an impact on your final or overall result. So now moving back to today's topic, what we'll be learning today is an artificial neural network. So the objective of AI and machine learning has been to design machines that reach the same level of intelligence as humans. In this regard, one aspect considered was to mimic the way humans process information. We designed an artificial neuron that essentially performs the same function as a human neuron. So we created a digital neuron that can replace or that can do the same things as a human neuron. The human brain is composed of 10 billion neurons which perform various functions. And each of these neurons is again connected with multiple other neurons in order to transfer the signal and get the jobs done. So looking at the anatomy of a single neuron, we see that it is comprised of cell body. Cell body is the part where the actual functioning occurs or some decision making occurs. It has dendrites. These dendrites are responsible for receiving the signal. So these edges over here that you see, these receive the signal from either other other neurons or other parts of the body, and then there are axons which pass the result of whatever the calculation has occurred inside the cell body to the next stage or next part of body. This can again be some other neuron or some activator which would act upon it. So giving you a brief introduction, an artificial neural network or an ANN is made up of artificial neurons. These are digitally modeled biological neurons. So we use the exact same concept for human neuron and found the closest match to it in the digital world. Each input into the neuron has its own weight associated with it. So looking at this example, I can say that first I created a cell body. So I've created one unit that is capable of receiving inputs. These inputs that we receive are equal to the one that dendrites were providing us. And then we produce some form of an output. So that's how we mimic the real world neuron into a digital one. Then the other part, or weight association. So please remember that once we did the linear regression, we said that even though we have multiple features or multiple properties that we can use, not all of them have the same importance to us. So that assumption or finding holds true in the rest of the machine learning algorithms as well, that once we do have the inputs, all of the inputs should not have the same importance to us. Some of these have higher weights, some of these have lower weights. So we've got inputs, and which would be usually specified as X, and with these inputs we have some weight or W properties. as each input enters the nucleus, it is multiplied by its weight. So similar to linear regression, what we see over here is that each input and its corresponding weight is sent in for further processing. So the nucleus sums up all of these input values. So the job of the nucleus is to find the weighted sum of the inputs. So what it does is it finds the sum of the inputs, but it's not a regular sum of the inputs, it's the weighted sum. So we assign some value or importance to each input and then calculate the sum of all of these. So this value or weight can be either 1 or the complete input is let to pass as is, or it can be something as 0 so as to block the input completely, or it can range in between these two. For n inputs and n weights, the weights are multiplied by input and then summed, which is why we call it weighted sum. The next thing over here we see is the equation for it. Now, this is the equation similar to the one which we saw in the linear regression as well. So we've got some inputs and some weights, and we provide a complete summation of all of these. In linear regression, doing this task was enough for us to produce output. So this is the part where your linear regression sort of ends. We calculate the weighted sum of all of our values, and this weighted sum is given as output of our function. So if I stopped my algorithm over here, I'll end up with something similar to linear regression. Then how is the ANN different? What the ANN does is that it performs some sort of function on the weighted sums. So we say that if the values of the weighted sum are significant enough to us, if they mean enough to us, then we produce some output. If they are not important enough to us, then we do not produce the output. This concept is again similar to the one that we have formed from the human brain or seen in the human brain. The human brain only lets the output or produces the output in cases that the signal is sharp enough. So if you touch a hot object but there is an insulation between your hand and the hot object, then not enough heat reaches you, so your body does not trigger a reaction. In case you directly connect to the hot object, then enough amount of heat reaches your body to explicit some form of a response. So again, what we are saying is that if the value is greater than some limit, then we produce the output. So the value that we are talking about is in technical terms called activation. So on the weighted average that we had, we perform some action to see what its value is, and if this value is higher than some threshold, higher than some fixed limit, only then our neuron produces an output. So we've got some function. If this function passes our criteria, then we produce 1. If it fails our criteria, then we produce 0. So the output is either 1 or it is 0 based on what the value of activation has occurred. Activation above a certain range produces 1. Activation below a certain range produces 0. Now this sort of a function that simply has output 0 and 1 is usually called a step function or a threshold function. A step function, because of what it looks like, it simply produces 1 for certain values and 0 for other values. Combining all of these, what a neuron looks like is it would get inputs with some weights. It would do a weighted sum of all of these inputs. Then it will have some function to evaluate these inputs. If the function produces a value bigger than what is required, then we produce the output. So what we have is an activation function that gets values from the inputs that are put into that are again passed through some mathematical function to reach here. Right? So I'll summarize this once more. What we have, what every neuron holds is some form of inputs, which are again weighted inputs. We perform some summation on these. After summation, we perform some activation function, the G function that you can see over here. This G is produced on the weighted inputs. And if this G produces an output or activation that is higher than some form, then we produce the final output. Okay? So this G function would give me activation value, and if this activation value passes my threshold, passes my criteria, then I produce the final output. So I can mathematically call the step function as this. If the sum of all of these values is greater than some threshold, then we produce output 1, and if it is lesser than some threshold, then we produce output 0. Moving on, this is the final equation that I just displayed to you in the previous slide. x1 is multiplied by its weight 1, x2 with weight 2, and so on and so forth. Now, please remember, this is equation similar to something that we saw in linear regression as well. So this is not something completely alien to us. We are known with this concept that we get the inputs and we assign some weights to that inputs. Now I can also say that if I brought the threshold over here, remember I've simply moved this from over here to over here, and I'd say that if all of this minus the threshold is greater than 0, then we produce output, and if it is less than 0, then we do not produce output. Okay? Where we assign W0 equals to T and X0 equals to 1. Here I'd like you to keep remember the reference that we did in linear regression, that with all of the weights we usually have one biased weight or one extra weight known as the biased weight, which in the terms of line equation we call as the y-intercept. And in order to fit this biased weight, what we had was a x0 or a zeroth input, and this zeroth input was assigned a value 1. So the complete equation would become something like x0 w0 to x and wn. One more thing that I'd like to talk about before we go forward, what the n over here specifies. The n over here is equals to the number of inputs I have, and the number of inputs would determine the dimensionality or complexity of the solution. So the number of input, and the number of input I am talking about is not the amount of examples, rather the amount of features each example has. So n is equals to the number of features each example has, and since the number of features control the dimension d, so it controls the complexity of the solution. The second thing to note over here is that none of the inputs here have power greater than 1. So it is again a linear solution. Okay? So far we are still in the domain of a linear solution. So this D would produce output if the final result of all of these is greater than 0, and this would produce output equals to 0 or nothing when it is equals to or less than 0. Some of the usual activation or functions that we use in our neuron are step function, the one that we just saw. It has two outputs, 0 and 1, based on the inputs. Then there is a sine function. Sine function has again only two outputs, but these are not 0 or 1, these are -1 and +1. Then there is the sigmoid function. The sigmoid function is different from the step and sine function because both of these are discrete functions. Okay? These are discrete functions, whereas sigmoid function is a continuous function, and this is not like a C. There we go. And again, linear function is also a continuous function. So the sigmoid function does have values between 0 and 1. Okay? Its range is again 0 and 1, but these are continuous values and not discrete values as in step function. Whereas a linear function produces whatever the input it was. So please do look at the mathematical formulations of these. So a step function has a discrete range 1 if x is greater than or equals to 0 and 0 if x is less than 0. A sine function has +1 if x is greater than or equals to 0 and -1 if x is less than 0. Whereas a sigmoid function has 1 over 1 plus e power minus x. So it produces an output between 0 and 1 in the continuous domain. While the linear does not do any processing on x, whatever the x is passed on as y. So the summary so far, this is what a typical neuron looks like. It receives n inputs. All of these inputs are multiplied by some weights. These inputs are not used as is. These are multiplied by some weights. Then based on these weights, we apply some activation function. The activation function determines whether the output would be produced or not. If the result of this activation function is greater than some threshold value, then we produce output. And if the result of this activation function is less than some threshold value, then we do not produce the